All right.
Right. Can I stand over here? Is that okay?
I can remove the stand. This one. You can stand wherever you want.
Excellent. Hello. So my name's Ian Cooper. This is a little bit about me. There is nothing on that slide that's really that important apart from this last point on the bottom, which I kind of always refer to. And that's that I don't claim to be any smarter than anybody else, right? I just happen to be happy standing up, speaking in front of a room full of people. I got here by starting out by talking, doing small lightning talks, things like that. I would encourage you all to speak. You all have something worth saying. The trouble is most of you think you don't because your peers, people you talk to, know the same things you do. They all do because you talk to them all the time. Lots of other people don't. They want to hear what you have to say. It's really great to help you organise your own thoughts and building your confidence level you're talking about. And I would encourage you all to speak less of me and more of you.
And if you have something to speak about, just let me know. I'll put you on.
I work here. You don't really care about the fact that I work at Huddle, apart from the fact that Huddle is a software company using software. I'm not a consultant. I have nothing to sell you. We'll talk about a number of things. We'll look at availability, what we mean by availability, what is that, can we define it? We'll talk about some tactics that you can use to ensure availability. And we'll talk really about a big topic, fault recovery. So fault recovery is kind of what you'll be most interested in trying to understand. And that's where we've got to talk about things like timeout, retry, circuit breaker, those kind of things you may have heard about. Things Netflix is very big on talking about. The first thing is, what is availability? What do we mean to say something is available? Right? Let's start a little bit earlier and talk about what we mean by fault. A fault is pretty simply defined as something going wrong. And essentially, a bug is the fault that we most understand, right? You get an error report from somebody, you say, there's a bug in the software, and I do this, this, and this, it probably breaks. But maybe also some of that poor performance. It could be simply that when I load this page, it takes 30 seconds actually to load. Right? So it's anything where really we say the software is not behaving correctly. And an error is when that fault causes us to deviate from the specification of the system. So we're saying, well, actually, the 10 seconds number, that's fine, because we accepted that this thing will basically take 10 seconds to load, and we've got a nice thing going up, and that's all fine. And we may say, that's way outside the bounds of what we agreed with the customer, that's definitely an error. Usually, it's a yellow screen of death or something, it tends to mean that's an error. If the application crashes, we tend to accept that's actually an error. So those kind of exceptions that get thrown and not handled are obviously errors. But what you need to understand is that any exception you throw is probably a fault. If you catch it, it probably may not become an error. Normal faults are quite important to understand. Sometimes we find that something is only a fault under certain conditions. Load, concurrency, more people in the system at any one time. So, it's very common to find these things high until you actually meet the error condition. It's one of the ones, that we have spent a long time testing for often is multi-user problems, when there are multiple users actually working on something at the same time. And you have hundreds of people bashing away, you can't find an error, and then essentially it goes into production, and lo and behold, you get some concurrency. Right? And those are the current on load as well as what important, right? So the system works fine when we're testing it. We had 2 testers logged in, so it turns out when 1,000 customers log in, it's a problem. Well, it turns out that when customers request their order history and they've got 100 items, that works fine. When customers request their order history, there's 100,000 items, our software breaks. We didn't anticipate that being a requirement. And we had some kind of one-to-many relationship with an ORM, went away and loaded all the child records and so failure is when that deviation from classification of the system becomes observable in some way. So somebody somewhere has noticed that something has gone wrong, and they are probably complaining to our support team right as we speak, saying, I can't get in and do my work, you've ruined my life, you bunch of amateurs. So not all errors are failures, because in some cases you can mitigate that fact, right? And what we'll explain later is how to mitigate some errors, so that they're less observable to users, or at least degrade the functionality that they are less aware of what's happening. So a classic case with that might be we serve results from cache, we can't get the database. The user may not be aware that the list they're looking at of tonight's shows on Netflix are actually an hour old, he's missing a couple of episodes have been released, but you may never realise, right? But you mitigate essentially some errors with that. So the usual definition of availability is that the system is not in failure. So you could have faults, you could have some errors, provided you're essentially providing service to the users, you are set to be available. And so the availability of the system is its ability to mask errors, such that effectively you continue to look for the user as though providing service. This is a usual measure of availability. You guys all heard of these measures? We get quoted like a lot, like 2 nines, 3 nines, 4 nines, and that tells simply what your uptime is. So the availability is measured as a percentage of time you're up, and that equates to these kind of numbers basically a year or basically a day. Usually the downtime is measured over a month or a quarter in terms of basically an agreement with a customer. So what in this one, that's 99.95%. That's what essentially the standard is for an AWS EC2 instance. Running one of those zone. Right, that means it offers that availability, that up. Is a pretty good number for a kind of SaaS business to kind of target. 4 nines is hard work. Generally because you get irritating things like we lose time for not things that are outside our control. So we have a data center. I'm not going to name names, but Carpathia, which was a US company, which also used to host kid.com. And they were changing a light fitting, well, a contractor, as the Americans would say, in other words, an electrician they'd hired came in and said, I don't want to be electrocuted. I better basically turn off, essentially, the electricity at the fuse, threw the wrong switch and turned the power to the entire data center, thus essentially preventing our software from doing anything very useful. And that's kind of outside your control. He was found an hour later by security hiding in a cupboard. Obviously kind of aware of quite what he'd done. So it's really hard to get this because you have to have so much under your control to actually achieve that kind of uptime. Right, so how do we improve our availability? Did the Norwegians get Animal Farm, or is that, no, it's not something you have in your kind of school? That, oh, you do, okay. Prevention, detection, and recovery. So what we really care about is how do we stop faults happening in the first place, right? What can we do to be less faulty? When they do occur, how do we detect them? And then how do we recover from them once we've noticed them, right? So the 3 main steps. So
The first step really on the road to health is just good practices in terms of the way you write code, right? And a list of things that you might put under the generalized heading of software craftsmanship. So let's do some TDD. Let's pair, because then we get two eyes on it. If we don't feel like pairing because we're uncomfortable with that model, let's be side by side and have some code reviews instead, right? Let's make sure we test, right? So as well as just basically the developer tests running, let's actually have some automated tests run by QAs or some exploratory testing. Because some things like concurrency errors from multiple users are actually quite hard to flush out with just developer tests, or even automated tests can struggle a little bit, right? So we want to flush some of those things out. Random behavior that essentially generates errors in the system. Those all will help us catch defects in the SDLC. Training, right? So you talk about the kind of things we're about to talk about today. You can essentially help people fix availability errors. But the reality everyone has to face nowadays is that faults will escape that process, particularly dormant faults. So the issue with dormant faults is that, essentially you quite often don't run your system in a QA environment in the same load characteristics or environment that you will run in a production environment. And therefore, dormant faults will tend to sneak into the process. Okay? So, generally speaking, nowadays, in distributed systems, we've come to accept that there is very little chance of us removing all errors from the process. There's this notion that faults will occur at some point or other. So what are you going to do about the fact that you need to accept that? This one is stealth mode faults. So there are some additional things, in case you don't know, that you can do to basically capture these dormant faults. As you said before, generally they come from issues like concurrency, from data growth, from resource leaks, right? So there are generally standard tactics. Multi-user testing helps you flush out concurrency issues. Soak testing, when you run your software, basically test environments over a long weekend, for example, and check before and after to see whether you've been leaking any resources. And load testing, where essentially you look at putting lots of load in your system. Those things will all help flush out the results. Okay, but even so, faults happen, right? So if things escape basically faults are going to happen, the next thing you need to do is detect them. So a lot of effort goes into the idea of saying, well, I need to be notified about faults when they occur so I can determine the health of my system. Okay? And what you really need to do is have a program where you think about how you're doing your monitoring. So the basic level is kind of logging, and obviously logging out errors. And if you have a distributed system, obviously you need to think about logging with something like the elk stack, because you don't want to be hunting through lots of individual log files located on various servers. You want to centrally collate those and then be able to effectively query those logs to determine what's happening. Okay. Beyond logging, there are more intrusive forms of monitoring. So you can check things like memory usage and see whether your machine's running out of memory. You can check things like disk usage. You can check things like queues. So if you're using something like RabbitMQ, for example, as a broker, you can check queue lengths. You can see that queues are basically going down at a reasonable rate, so work's being processed to check that nothing has stalled, for example. You can check the database. You can look for things like head blockers, which mean that essentially nothing else is being processed or something's being deadlocked. There's a huge amount of monitoring you can do, and generally what you're looking for is the system beginning to behave out of its normal characteristic envelope, so that you can begin to suspect that an error is occurring and you may need to essentially mitigate it. Okay. There's a whole range of tools called application performance management tools, and these essentially look at giving you a kind of dashboard view of your system. So classic examples are things like Nagios and New Relic. Any of you use those? Yeah. Okay. These basically plug into your system and essentially provide you a large amount of data about what's happening. Typically, what happens is they give you monitoring information on any of your servers, on the application runtime itself, and then you can set up information around key business transactions, i.e. key journeys the user makes, and you can determine whether or not essentially they are performing with what's called an AppDex score usually. So that says, I set some limits for how fast this should happen, etc., and then I report issues which basically come outside that score. And generally you'll get alerts popping up saying, you know, this particular transaction is essentially running much too slow. And then you can go and investigate. The application performance monitoring tool will often give you an indication of a timeline. You can say, give me the information from the last 3 hours. You look for spikes in the graph, etc. So we may, for example, get alerts at Huddle when we get particularly unusual heavy traffic. Someone starts uploading piles of video to the site. We may see alerts as basically parts of the system start to struggle under the load. And then you can react by introducing new capacity, for example, into the system in order to cope with that temporary load. Okay? That's application performance monitoring. So if you can't eliminate your faults, then what you need to do generally is provide yourself with protection when those faults do begin to occur, right? And so if I detect things, do I have the ability to actually then deal with the issues? And what we're really concerned about is to prevent propagation from one part of the system to another such that effectively you get failure which is visible to the user. Okay? So particularly in distributed environments, it's quite possible for one component to begin to behave in an aberrant fashion, but us to simply use other capacity to replace that, or to essentially cope in the caller by serving results from a cache, for example, and prevent failure. And this is what we're going to talk about mostly, is what are these patterns you can use to achieve this kind of level of resilience in the event of failure. And what you're seeking most of all to prevent is what's called a cascade failure. So imagine we have a system which is basically which has components A and component system A and system B, and B depends on A. I have to get this right way around because I always forget which way I've said it. So B is depending on A, right? And a fault occurs in A, and that fault is unhandled. So we throw an exception because, for example, a sequence is empty and we didn't expect it to be. So that exception effectively, and the fault becomes an error because it bubbles out, right? And that the system itself then says, well, I don't have any way of coping with this, and it fails to respond to the caller. Okay, so B has called A in a reasonable expectation that A will succeed, and now it's throwing back an error. So if it's basically making an HTTP request, for example, you're hoping for a 200 OK back, but actually I'm giving you back 503 internal server error. Okay, so system B now has a fault, and its fault is that system A is not behaving as it expects to. Okay. The problem becomes if in system B we have not written our code to anticipate that that call to system A could result in an error, i.e. 503, we get no results, and it simply then fails in turn. We have a new fault. That fault turns into basically a error on system B because it says, I don't know how to cope when the system fails. And it then propagates out by failing itself. And that can go all the way up your chain. That's basically a cascade failure. Okay, everyone kind of got that? So most of the patterns we're going to talk about are really focused on preventing cascade failure. Okay, so at this point, anyone flying in a plane tomorrow? If you're flying in a plane tomorrow, you might want to basically go to the toilet for 2 minutes while we talk about this. So I'll talk about an example from outside of computing because it's a really good way of illustrating a cascade failure. So DC-10 in 1989 crashed in Sioux City, Iowa, and what happened was the fan in one of its engines developed a hairline crack. And that crack, essentially, under stress of the engine being in use, effectively caused the fan to disintegrate explosively. And as the fan at high speed effectively tore itself to shreds, it threw fragments of fan through the rest of the aircraft. Back in 1989, some of you may be young enough that effectively you don't really remember 1989, aircraft didn't fly by wire, they flew on hydraulics. They used fluid basically between the controls and the control surfaces, and these hydraulic lines were severed by fragments moving at high speed. That meant that the aircrew lost control of the control surfaces of the aircraft, right? So they couldn't use the flaps and the rudders anymore to steer the aircraft. So their only option in order to deal with the aircraft was essentially to throttle the two engines so that they could vary the speed in order to help them steer the aircraft. I'm going to play a video. Is that going to work for you? Okay. I'm going to turn up my sound. I don't know whether you better hear it all, but we can. Oh, I don't have any sound coming out. Never mind. We'll see what happens. That's just a ground alarm going off. The most amazing thing I think about this particular accident is that a large number of people walked away from the accident. And they first they thought that there were no survivors, and then they discovered that most of the survivors were parts of the fuselage that ended up in cornfields. This is Iowa, just beyond, and they came walking out of the corn. They discovered the pilot's still alive. The wreckage that the pilot plane there was so twisted and mangled that they just thought it was a lump of metal, and two rescuers were actually sitting on this piece of metal, taking a break, eating their lunch, when they heard tapping from inside the piece of metal they were sitting on, where the pilots were actually trapped. So 111 died and 185 survived, which when you consider the seriousness of the accident. The guy called Captain Al Haynes, who was the guy flying the aircraft, became a hero. They essentially tried to simulate what he'd done, basically throttling the engines on the aircraft to land the plane again, and no one could successfully land the plane in the simulator. They always crashed short of the runway. So for that reason, it's become known as the impossible landing. This guy is Lieutenant Colonel David Nielsen. He was a National Guardsman on duty that day, and he's carrying basically this child away. And this photograph went around the world. There's a statue now basically in Iowa, basically of this image. And people didn't really understand what had happened. The next day, Lieutenant Colonel Nielsen went to visit the hospital where this child was to speak to him, and a reporter shouted out, "You saved that child." And he replied, "No, sir, God saved him, I just carried him." There you go, that's cascade failure for you. Maybe not flying. Anyway, but the good news is, right, people survive in quite large numbers, crashes like that. Okay, it's about fault recovery. The most basic pattern in fault recovery is the timeout. Okay? The idea is that if I essentially call from one process to another, I am generally going to be using resources on the caller while I wait for the callee. Eventually, I will run out of resources. This is true even if I'm using some kind of async process to do that. I effectively do have resources tied up in the call, essentially. So eventually, I will run out of resources. Eventually, I'll run out of resources and I will fail. Okay? So, imagine that my system is set up as follows. This is my user. There's essentially a front end, takes an HTTP request, some kind of web server. It's calling some kind of microservice on the back end, probably via HTTP in this particular example, or the TCP IP or any other kind of synchronous call would work, and it talks to the database to get results back. So imagine that essentially when I'm calling a database, I have a number of long-running queries going on, and as a result, there are no connections left in the connection pool for the microservice, so to speak. Has anyone ever had this? Okay, so occasionally you can run out of connections in the connection pool. Okay, the problem is that if I don't do anything about this, then what happens is I will begin to run out of threads on this service, which essentially is now waiting effectively for the resource pool to come free. Okay. And so what can tend to happen is this becomes starved, and this basically stops receiving any new requests from the first service. Oops, why am I not? There we go. You then tend to find what happens is that your web server, you've got incoming requests coming from your customers still, begins to essentially say, well, I can't actually make any calls out to this service anymore. I'm blocked on doing that. It's basically, I'm now waiting for it because it's constantly telling me it's waiting still, right? So eventually what happens is it begins to queue requests. And after a certain limit, your web server will tend to say, I can't queue any more requests. I'm going to tell the users that basically I am broken and down, right? So this guy waiting here, effectively never actually giving up, causes this guy waiting here to never give up, causes your server to actually run out basically of capacity, and your users see an error. Okay, and it's easily fixable. I just time out, right? I time out when essentially I am waiting to get database connection, and I say give up after a certain amount of time. And if I time out and I get a lot of timeouts, what I can do is actually signal to my users that I'm under load. give them a 49 too many requests, and ask them to back off. Okay. Or enhance your calm, I think Twitter tells you. It's a very simple fix to the problem. Okay. Anytime you're really making a call between one process and another, you should time out. Okay. And one of the problems with some older frameworks is that their timeouts are ridiculous. By default, they're kind of like 2 minutes. 2 minutes is an eternity in modern computing. You know, your timeout should be something like 500 milliseconds or something, not 2 minutes of sitting there going, gee, no one seems to be replying. I wonder how long this operation takes. Okay, so have a reasonably spaced timeout. Oops. Okay. Does anyone want to play? Want to play some balls? Come on. Can I just get? Let's have you three, right? Come on, up the front. You've all had a beer. At least 2 of you have. So that should give you some courage. All you have to do is throw and catch balls. So we just demonstrate this. So the reason we do this is because teaching things in different ways helps. Form a line in front of me. Ready? You are going to be our web server. Step forward a bit, sir. You are going to be our microservice. Congratulations. You're going to be our database. So we're just going to practice. I'm going to throw the ball to you. You just throw the ball to him. You throw the ball, and we just all go all the way back. Very simple. Don't worry if you can't catch. That is just a fault. We are dealing with those. You can pass the ball back, database server. You can respond to the request. Database, you can throw them back. Nope, respond via the guy in the middle. That's it. Well done. Okay, and I've dropped the ball, just so you know it happens. Okay, so what we're going to show now, first of all, is this guy essentially holding on to all the balls. Essentially, what we want to demonstrate is that you're not responding at all, right? And you'll see, effectively. Okay, so when you get 2, actually just stop when you get 2. There you go, sir. Right. Now your hands are full, right? So you're not going to respond to any more requests. When you get it now, hold on to the balls. Okay. He's now full as well. So what's going to happen with this guy, if we have more balls, is essentially he's eventually going to run out of hands and he's going to stop responding. Okay. Now, what I want you to do this time is I just want you to count to about 3, and then just start throwing the balls back, right? So the requests come in, the database is effectively going to start filling up. Other one for the database. Okay, the database is now blocked. He hasn't got any resources left. So he's going to count, right? He's going to time out. He's going to say, hang on a minute, and he's going to pass it back to the web server. 1, 2, 3, right. So he's timed out and said, hello, I couldn't service that request. So these guys can keep playing, right? Eventually the database becomes free and he throws his balls back. Great. Oh, fault. Thank you, guys. Right. Don't worry, you'll get your turn. So the reason I do this is because it helps to learn things different ways, right? And as they get a bit more complicated, they get more kind of interesting. Okay. Retry. So it turns out that a lot of the faults we get are actually transient. We get occasional network errors, right, which just happen. And then if you try again 200 milliseconds later, then the fault is not there, right? Databases have things like deadlocks, which occur momentarily, and then they're gone. And so the problem with timing out all the time is that essentially, well, I've failed a request for that particular user. Maybe I've given them some results from cache that are stale. That may be a sensible thing to do at that particular point in time. Well, I've kept the system running for the majority of my users. I may well have given a degraded experience to some user when I could potentially have given them a better scenario. And in this particular case, what we're saying is effectively, rather than basically, we just got a deadlock, right? So in the case of a deadlock, maybe we want to try something else. And the answer is to retry. Okay? We just retried that particular operation at that point in time, then effectively it would flow correctly. All right. Let's have, come on, you 3 can come and do balls. Don't worry, come on. Yes, come on and throw balls. I'm usually one that drops them, so. Right. So, person in the front, you are a lovely HTTP web server, you are a lovely microservice, and you are a lovely database. So what we really want to do is just, first of all, we'll start off by just repeating the scenario of just some normal progress. So you guys get used to it, just throw a ball up and down so you guys can feel up to speed, just throw it all the way back. Excellent. You're operating reasonably well. Oops. Okay. Right, so now we're going to do a retry. So all I want you to do, really, is when you've got two balls, you're going to stop receiving requests. And then when you come to throw to him, you just want to count, and then eventually just throw a ball back while she's still counting, effectively, and then she can throw her ball to you. So just say, you count to 3, you throw the ball back, you're freed up. You can get the ball that's coming back to you, and then he's free to take a new ball. We'll see, watch. So you can catch two balls, keep going down. Keep going down, all the way down. Right, database is now busy, okay? When you come with this one, okay. So you now can't throw to him, but if you count, 1001, 1002, 1003, now you throw the one back, he's freed up, you can throw that green one forward, and can you see essentially the retry means that we are effectively able to keep servicing the requests. Let's do it once more. 1001, 1002, 1003, and then effectively it's free. Right, very simple. Thank you very much, guys.
Thank you.
They get more complicated as they go on. Okay, very easy. So, generally use a retry if you're aware that the fault is transient. Quite often, if you are receiving an exception, you may well have a really good indication as to whether actually that fault could be, whether you could retry. Sometimes we code some of our APIs to give you actually a retry basically after a header back to say try again this amount of time. Don't retry if you're aware it's not a transient error, right? That's just kind of crazy. Also be aware that you need a limit to the number of retries. Generally you should be guided whatever your quality constraint is for the overall service time of your particular call. So we have a rule, for example, that any API call should complete under 300 milliseconds. And generally, if you're going to push yourself way over that, then you want to think about whether or not, essentially, you should keep retrying over that period of time. Okay. So what do you do if you've got an error and that error's not going to go away for a bit? Okay. So the database server has failed. The cluster manager is busy desperately trying to basically bring up a new database for us. But we want to, in the interim, try and avoid the problem of either lots of resources being consumed by us waiting to do timeouts, or lots of retries trying to hit the database when the database is already suffering. Okay. So let's imagine essentially that we have, again, essentially not enough connections being free from the pool due to long-running queries. The last thing we want to do is to keep hitting that database to make it harder. The problem with essentially our model of effectively fixing this whole thing with a timeout is going to be that we're just going to consume resources here for the whole period of time, right? And we might just want to say, actually, you know what, we'd be better off coming back in a little bit of time, having a gap and saying, let's just basically fail anything that comes in for the next 2 or 3 seconds, and then we'll start trying again. That's what a circuit breaker does for you. A circuit breaker essentially says, I've seen a number of errors from the component that I'm talking to, and because I've seen that number of errors, I think that component is faulty. As a result, what I want to do is stop sending it requests to give it a chance to recover, or give the ops team a chance to recover that item. So I'm now going to do what's called breaking the circuit. So obviously, it refers to kind of the electrical concept, right? We'll play balls in a second, but generally we think of 3 states for a circuit breaker: open, closed, or half open, right? When a circuit breaker is closed, that's kind of normal operation. Traffic goes through the circuit, okay? When it's open, we stop traffic going through the circuit. When we're half open, what we're doing is we're saying, maybe it's fixed on the other side now. I will push through a test request. If that generates no errors, I will then close the circuit and allow traffic through as normal. If that breaks the circuit, if that fails, I will then break the circuit basically and open it again in order to prevent traffic going through. right? So the idea is to give breathing space to the component that's potentially under load or suffering by essentially breaking the circuit. And normally speaking, what you would do when you have a circuit breaker trigger is you push back some kind of error to tell this side that basically the circuit is broken, and then it knows essentially to tell basically clients to back off, serve results from cache to the user, and otherwise code, right? So this particular circuit breakers became quite famous because Netflix's Hystrix library, which is what it uses essentially behind its API, provides a circuit breaker capability for you. And that will essentially, when their circuit breaker triggers at Netflix, this serves results basically from cache. And what they do is they record calls into here, and they record essentially the parameters on the call. And then what they do is they say, if someone else is making the same call with the same parameters, I will simply serve the cached result set from what I got last time in that particular circumstance, right? So it's a way of dealing with caching. Okay, I won't make you stand up and do circuit breaker, because it's a bit like retry, only effectively we do a half open, half closed state. All right? Oops. Come out. So it's a way of us essentially preventing us from locking up resources when there's a long outage period on some kind of component or fault in our system. Decoupled invocation. Okay. So we may find that our inbound traffic to, for example, our API becomes sufficiently great that when one of our components begins to think about failing. So let's say our microservice really can't cope with a number of requests. It's doing some complex work. Perhaps it's basically stressing the CPU a lot. And the rate of requests coming in over HTTP API is too great for it. Okay. In that circumstance, essentially the problem will be that I will fail here. So what example have I actually got here? Right, so I've got a DB connection pool exhausted by long-running queries again. Okay, fault, and we've seen that scenario before. So what I can do to alleviate this problem is introduce messaging. So if I introduce a message broker or some other queuing system, I could use something like 0MQ to be fair. Or, if I use messaging between my HTTP API and my backend service, then effectively I can use messaging to throttle. And what happens is that messages that come in here, I acknowledge them and put them on a queue. I go back to the user and say, I've received your request. I'll probably do 202 accepted. And say, I've received your request. And I may give them a link to say, go to this link, here's part of that 202 accepted, and you can see completion of your request there. Okay. And then generally what happens is on that link I give you, there's some kind of monitoring endpoint which says, are you done yet? And that may even redirect when it's finished to the actual resource that you were looking to basically deal with, right? And this message queue essentially has basically guaranteed delivery, right? So that means essentially when I put a message from here onto here, it's basically, I know that it's going to be delivered at some point. In other words, it's basically a durable queue and it's persistent. So at some point, the message will be delivered. And this back-end service then consumes at whatever rate it feels it can handle. Okay. So if suddenly I get a surge of traffic, what happens is my queue just builds up. And I process things a bit slower. The consequence is, of course, that you are effectively suffering from eventual consistency, because the user may effectively have got a response back saying, yes, that's all very good, etc., but it may take a while before those things feed through. One trick sometimes is people actually at their front end treat things as though they've succeeded and let the user move on, even though the back end hasn't succeeded because they just changed their local state on the front end. Okay. But this service on the back end is able to basically throttle. So this is an alternative to introducing huge amounts of new capacity here, right? What I can actually do is say, you know what, I'm just going to use the queue to throttle my traffic. All right, let me demonstrate this one. Let's have U3 again from this end. Come on, out you come. All right. This one is very easy to demonstrate. So we'll just throw the ball once up and down just so to get you warmed up. Right, here's what we're going to do. you are now basically going to have a message queue as your input. So I just usually just use your t-shirt. As the balls come to you, just shove them in your t-shirt. All you do with database is casually, whenever you feel like, you can just take one, work on it, and then pass it back up the line, right? Don't rush. You're in no hurry, you know. He stores that, essentially, storing it in his queue. And whenever the database feels like it, the database can pull one out, deal with the work in a leisurely fashion, and when he's done, pass it back up the line, right? You're guaranteed delivery. Don't be dropping them on the floor. Okay, great. And you can see essentially what we've done is we've alleviated the pressure on the database at the back end by using a queue. Thanks very much, gentlemen. Okay. All right. So effectively, if you worried about basically experiencing load, one way of dealing with load is essentially to have decoupled invocation. Decoupled invocation just means essentially I put work onto what's quite often called a task queue and get a back-end worker process. So this is when people start to talk about web processes or worker processes, talk about dividing between the thing that's actually receiving the request and doing work at the back end. It does require you to effectively be able to support asynchronous working, right? So either fire and forget or essentially a response occurring later out of time. Interestingly, as a kind of aside, there's an interesting white paper, which I can't tell you where it is at the minute, but some academics looked at the kind of event reactor pattern, which essentially is what Node.js is, where effectively it says, in the event that you're I/O bound, yield control back to the CPU, which will carry on with the next piece of work, etc. Right? And they looked at that and compared it to the proactive pattern, which says, actually, I've got multiple threads. I'm not, the V8 runtime. And so the multiple threads will just pull. So you still, when you're I/O, you hand your thread back, but then you've got multiple threads processing the new incoming work from the pool. And when they yield, they just hand a thread back to the pool for another piece of work. And then they looked at basically using task queues, which essentially is when the work comes in, I put it on a message queue and a back-end worker process handles it later. And they have essentially said task queues are always more efficient and easier to develop than the first two options. Okay, competing consumers. So one of the problems, of course, decoupled invocation is I may not be moving at a rate which is fast enough for my end users. Okay. So how do I actually use this pattern but go faster? Right. And the simple answer is I introduce multiple consumers of that queue. And this is essentially where we start to talk about being elastic, right? As my queue builds up, I effectively can introduce new consumers which reach from the queue. My queue has to support the idea of multiple readers and handing out different pieces of work to each consumer, but most modern ones like RabbitMQ, for example, do. And I simply get those additional consumers to all basically start processing work. Okay. So, similar scenario, basically. In this particular case, there's one piece of information we need to clear up. In the previous one, the problem was our database is under too much load, right? In this particular area, probably your problem is that an individual CPU is under too much load. If a database basically is going to struggle, it's probably not going to help you to introduce additional consumers because you're simply going to put more load in the database. So your scenario here is much more likely that you are bound by the CPU on this particular step. So for example, we use this for doing things like processing video, where essentially you're quite often CPU bound. All right. And you can see here, effectively, I've got my HTTP service, but now I've got effectively 3 instances of the microservice. And those 3 instances, essentially when they're running, all consume messages from the same queue and effectively divide the work between them. And that means essentially that I can actually then scale. Yes?
I have an example when actually it works with the database under load.
Yep, go on.
Not if the database is suffering from not being able to complete a request, but when the database has latency.
Right,
so it's not really loaded, but the latency prevents one consumer to perform the work fast enough. So by introducing competing consumers, they fight the latency because the combined latency will be smaller.
Yeah, and particularly if they're actually not trying to process the same rows, they can all effectively work on different rows. Well, so they can parallelize the operation.
Yeah, we use that with Redis because the speed of Redis is okay, but the latency to
So view 3 again, we can just run that particular scenario again very quickly. Come on. Because you know what you're doing. And we're going to have this gentleman here is going to join them to be our competing consumer. So same scenario again, I'll pass the ball to you, you store them, but just the two of you can both pick out of his queue, right? So it's very simple. So he's a guaranteed delivery queue, remember that. All right, there you go. So these guys can essentially just pick stuff out, and when they're done, they just throw it back, right? You may not be able to catch him, he hasn't got enough hands, but you can put it back in his queue. Yeah, right, exactly. Right, thanks so much, guys. So it's very simple, right? You guys are much better at throwing balls than some of my normal audience who tend to drop them. I'm quite glad because there is an open window, and I was a bit concerned that balls might be flying out the open window, and I'd be seen tonight from a Norwegian jail cell while I tried to explain my behaviour. Okay, so increase the number of consumers. This is interesting, right? Sometimes it's really important that the items on your queue are processed in order. In that case, avoid using competing consumers, right? So if you have a queue where you need to process things in order, one of the ways you may better rely on the queue's ordering. But that depends really on your ability to guarantee that the sender has sent things in order. But if the sender's got multiple threads, what you do to deal with that essentially is you can put sequence numbers on the items in the queue, and you can simply say if an item comes in out of sequence, I'll re-queue it, and I'll deal with that one later. And that kind of works okay. But if you have multiple consumers, what tends to happen is that they behave very negatively because the first consumer gets item 1, second consumer gets item 2, and it says item 1's not been processed yet, puts it to the back of the queue. The first consumer then says, oh, there's item 3, but where was item 2? That hasn't been processed yet, right? And they reorder the queue very negatively, and actually things perform worse. So in that case, you only really have one consumer. You can have a hot standby if you're concerned about basically fault tolerance. And generally in failure, one of anything is bad. So what you tend to want is a second consumer to run that essentially says, I don't do anything, I just ask the other guy whether he's running, and if he's not running, I take over.
Competing consumers can still be useful if they are partitioned properly.
Yes, that is true.
Then they will not be conflicting to the order if they just do different things, well, same thing for different pieces of data.
Right, exactly. An event store, for example, Greg Young's product essentially is built to support competing consumers by partitioning effectively the data so that essentially they get different subsets of the data. That's quite useful. Okay. Parallel pipelines. Don't worry, won't make you stand up for this. It always ends in confusion. Parallel pipelines. So what do parallel pipelines say? Well, sometimes an individual consumer can take a really long time to process a given task. And what happens as a result of that is the queue can back up. So we see this a little bit when we're doing something like processing video or doing file conversion between formats. And everyone's sending us files which are basically, below a megabyte in size, and then somebody sends us one that is basically half a gig, right? And when we're processing that one, it takes quite a long period of time, and then what happens is everything else in the queue is backing up behind it. Now, competing consumers can help alleviate that because a new consumer starts basically taking something off the queue because, and freeing up basically other items. But even then what happens is, you get another item and you block that consumer. So you then keep basically pulling out consumers to deal with the blockage. So there's a bit of a simpler model than this, right? So you can actually say, well, what I want to do is parallelize the work. So here's what happens. When I make my request to my backend service, I start running a pipeline. And that pipeline has a data source and a data sink, all pipelines do. Data source says, right, the work that has come in, I want to effectively divide that up into individual pieces that I can then do in parallel. And at the end, I will essentially collate the pieces and effectively respond with the work, right? So essentially, this is a kind of MapReduce problem, right? And so each one of these particular items effectively says, I am basically a service. I basically I receive one of these pieces of work. Now, you could make the calls directly, but generally what happens is you have a message queue up and down the pipeline, And essentially you say, well, I've got a queue to here, a queue to here, a queue to here, and they all feed back into here, right, when they're done. And each one of these items is then able to run and deal with work. Now, what you'll find is then, you get smaller items running very quickly, and you'll keep processing parts of the work. So your speed is now governed by the slowest step. Okay? So you can never get faster than your slowest step, because you're processing everything else in parallel, which it takes less time than the slowest step. You can reduce the overall time taken to complete the work. So imagine that my overall time was, say for example, 10 seconds. Okay? And these steps all took 1 second, but this step took 6 seconds. Under the old model, we had previously back up here, is that a broker? Go back. We'd find that took 10 seconds, right? Because essentially each one of these is processing a whole job, right? Whereas if we go back here, we'll obviously find that it takes 6 seconds, because we now run at the speed of the slowest item in the work. So we can improve the performance of something that essentially is a problem for us by effectively distributing the work to a range of consumers that handle subparts of the process. And essentially the data source basically pushes them down basically via pipelines to each of these items, and then basically collate them at the far end. So it's this MapReduce model, right? Make sense? Get that? And essentially we therefore basically are only governed by the slowest part of the process, not by all the other bits. Okay. So that's essentially what we're doing. Yeah. So you can generally find these bottlenecks basically in some of these steps by effectively doing monitoring. You can see which ones are the actual slowest items that you've got. Okay. Cool. Right. Okay. So that's it for me for the patterns list. What else should you read if you're interested in this topic? Okay. So kind of the key book is this one. Has anyone actually read this book here? All right, I urge you to go and read this book. This book is the worst named book ever, right? Because this book has absolutely nothing to do with releasing software. So I do not know why they ever chose to call it Release It. That makes no sense to me. This book is essentially, by Michael Nygaard, is the major source of availability patterns, and it's basically a lot of war stories. It starts out the first half. He ran some exceptionally high volume e-commerce sites and about how they found, diagnosed, and fixed problems in them, and then a series of patterns and practices to use basically in building sites. So the popularity of things like retry, circuit breaker, etc., come from this book. This is the original source where people picked it all up from. And I cannot recommend this book highly enough if you want to essentially deal with it. There are a lot more patterns than the ones I've discussed here. I've kind of picked out some highlights, but there's a whole range of patterns and there's a whole range of effectively smells to look at to see whether or not your system basically is lacking availability, what the causes are basically of problems commonly. So we just said there's a fault. It talks a lot about what kind of faults you experience, what the causes are, and that kind of thing. So I really recommend reading that book. This book's probably still one of the best books, I think, about patterns to use if you're doing SOA, and by extension nowadays kind of microservices, right? And that gives you a range of patterns to deal with, basically. So stuff around decoupled invocation, etc., some of that stuff you'll find governed in here. But generally, if you're building microservices at all, I recommend reading this book. It's very, very useful for understanding how we build these things properly. Okay. If any of you .NET developers? Okay, so I work on a library called Brighter. We just got our non-beta version of our .NET Core version out. So basically we're a CQRS framework, but we also do task queues. So we basically give you the ability to pass a command over a queue. So we do decoupled invocation for you, right? And we can be used in microservice environments. We basically integrate with a library called Poly. Who's heard of Poly? Okay, so Poly is a .NET library which essentially supports retry, circuit breaker, timeout, and various patterns like that. So we integrate with that and basically let you control your pipelines for handling requests using Poly policies. Right? And so you may find that helpful if you're interested in this kind of stuff and going home and look at what we do. All right. Summary, let's talk about what we talked about. So we basically talked about what failure was. Okay, so failure is the deviation of system from specification. And then we said essentially that faults will happen. We should never expect to be able to ship a perfect system. We're going to ship something that's faulty. We said that the very basic pattern we should always basically remember is that when we make a call between two processes, we should time out. And we should not wait for all eternity because essentially that causes chain failure. We said that we may want to retry. We think the error basically that we are going to experience is potentially transient and will clear. And we said if we think the error that we're receiving indicates a long outage, we should break the circuit, serve results from cache, not put additional load on the failing component. We said that in the event that we're experiencing problems with load, we can manage that load ourselves by queuing through decoupled invocation. And then if we just speed up the processing of those items under load, we can effectively use competing consumers as a pattern, right? So we have some elastic scaling involved, and we can do things like monitor queue lengths and introduce new consumers. And if essentially the problem is that in our pipeline we have too long, it takes too long to process the work, consider splitting up that work into a number of pieces and processing it in parallel so that we basically only take as long as the constraining element in the pipeline. All right. Questions? Have we got any questions?
Right, so what does it use? Does it use any messaging means?
So Bright is built over RabbitMQ, and we also, in theory, support Azure and AWS, though our support is more patchy because we've had to rewrite since .NET Core conversion, because both of them had different libraries. I think the Azure stuff might be working, and the AWS stuff needs us to address it. Because in the .NET Core timeline, Azure's essentially, we're using a third-party lib and some REST stuff, and AWS changed their libraries, so we're not sure about those two, but the RabbitMQ stuff works. We have a kind of, if you like, a plug-in model for different providers, so you can write new ones if you want to. We may tackle, or I may tackle, because I think it's falling to me that one at the minute, doing it over basically Redis. And I think another group of guys in Holland were talking about building one over a SQL database, God bless them, because they can't get anyone to give them access to the bus inside the enterprise. So they're basically having to use a database which they can get access to. But yeah, so if you're using RabbitMQ, we are a really good solution. And we know it's exceptional. We know we do with very high volume, and we're very reliable. So we build a lot of reliability over it for you. So the model we have essentially is that you create a command, and you essentially do send if you want to basically target one handler, publish to many in process, but you do post if you want to basically target a handler out of process. And essentially, but it looks the same, so the handler looks the same wherever you deploy it. And then all you have to do is add configuration, and the configuration essentially inside your service that basically is consuming from the key, puts some configuration and saying, essentially a routine table saying what messages do I subscribe to and what handlers do they go to. And then we handle the whole thing seamlessly for you. So all you have to do is write your handlers. You don't have to deal with any of the infrastructure concerns.
I remember I looked at Bright, but for some reason I chose mass transit stuff.
Mass transit, is very similar, and service buses is similar as well. We all do a similar job. We just have slightly different opinions on how to do that job, but they're all equally valid ways of doing it.
Can I ask you, you said RabbitMQ, so we're using that as well. We have had some issues where basically RabbitMQ does not guarantee the delivery from the exchange to the queue.
Yeah.
So how do you handle that issue when we say without using transactions without RabbitMQ, because that kills performance?
Yeah, so what we actually do is Bright gives you the option to have a message store that the sender effectively puts to work in the message store. And we recommend generally that your message is bright and potent, and then you just resend from the store if the messages go missing. So we handle that. The only way you can detect that, though, essentially, is if effectively your system is no longer where you expect it to be in terms of state. We don't have any auto detection to check there's no delivery between the exchange and the actual queue. It is what it is, right? But we provide an additional level of safety, which says when you send a message, we will put it in. You can put it in a message store. We don't do a transaction. To do that, we essentially recommend generally you do that in 2 steps, and we've actually stored the message in the message store, and then we kind of send it, so that effectively in the event that you fail at any one step, you can usually recover back to pushing something out of the message store.
Sounds like Alpha.
Yeah, essentially a number of us do the same thing. Yeah. We also let you do what's called a command sourcing option as opposed to event sourcing, and let you store incoming messages basically on another side to say what did I receive. So you can support that kind of Fowler-esque version of event sourcing as well. But yeah, we just have a message store and say be idempotent, so you can resend stuff that went missing somewhere in the deep dark, so depths of rabbit. We tend to not use. We don't tend to, as a result, use messages that basically are persistent. And we also don't really quite often use durable queues. We tend to have our consumers create queues when they start up. And we just, as a practice, don't tend to, if we're basically having to do something which involves shutting down the exchange, we would tend to essentially make sure that we start and stop things in the right order, so that the consumers start operating before the exchange comes up. Then we have a lot of retry logic, which essentially sits there waiting for the exchange to come online and then connect to it. As a side effect, that really helps us in Docker scenarios, because when you use containers, what we discovered quite early on was that if you basically have a container with Rabbit, even though the container spins up, Rabbit itself was not basically started yet. And so when in your Docker compose file, you're saying, hey, I'm dependent on the Rabbit, on the broker, it just waits for the container to start. It doesn't actually know if Rabbit started, right? And so the result of that is that you quite often find people talking about saying, oh, my container's tried to talk to the broker, but the broker's not there and it's failed. We just basically retry when the event that happens after an interval. So we try and get around some of the limitations of the queue.
I find that quite interesting, because we're trying to solve a resiliency issue, having error and tolerance and retry behavior, and then we have to build around, do a pattern which involves a queue, and then you have to build, I don't know, any mechanism to handle any errors in the queue, so you end up adding a lot of complexity.
You do. I mean, the advantage of basically using somebody else's library that wraps all that is essentially that complexity then goes away from you, right? I mean, on the Python side, we quite often use Kombu, which essentially does all of that work for you anyway, right? But generally, when you're talking to message queues, there's a lot of this try and make it reliable issue going on. That even, it's just an issue. I mean, anything where you have the pattern where essentially you are a what's called a dynamic recipient list, and that means that the broker subscribers basically are dynamic. In other words, basically they at runtime appear and say, I want to be a part of the recipient list. In other words, basically I subscribe to that particular kind of notification. Has the risk that effectively a given consumer won't receive a message, and that's why we basically let you resend, because that's the easiest solution to the problem, is to basically make sure that we capture the outgoing traffic so that you can just resend it. And that gets over any problem that kind of ordering and reliability. Are you clustering or?
On Rabbit?
Yeah, on Redis, Rabbit, yeah.
Yes.
Yeah. So I think, I mean, that's usually okay, but I think you get more issues actually with the cluster sometimes in terms of basically losing stuff. Sorry?
Partition cluster.
Yeah, and that's when you tend to lose messages usually.
We went back to single instance.
Yes, I think some people do, right? Bizarrely, you may be better off effectively, just going back to one instance, but that's a weird thing. I don't necessarily know of anything that's ultimately better. They all have their weaknesses. Whose blog is it? I can't remember now. Whose blog is the one basically is closure scripts basically? Is it AFA's blog essentially? If you haven't read AFA's blog, AFA basically is quite a distributed system guy, and essentially he goes around testing distributed databases and queuing systems and breaking them in interesting ways, and essentially proving that many of them violate the guarantees that they give. So if something is guaranteed to be available and partition tolerant, most of you familiar with the CAP theorem, right? So CAP theorem says consistency, availability, and partition tolerance, you should choose two. Although Bureau of Disputes, he says that, right? There's a paper called 12 Years Later, where he says, actually, I didn't quite say what people think I meant, I said, but. And so what AIFA has been proving is that some people basically say we're available and partition tolerant, and quite often they're not as partition tolerant as they claim. There's a lot of, cap theorem is very interesting, there's a lot of nonsense talked about cap theorem. For example, people say, oh, you can't choose consistency and availability, right, at the same time. You can, right, but basically what that means is essentially that you're probably saying, I've got my SQL database running in a data center, and I don't have effectively the ability to cope with essentially a partition because actually all of my kit runs in the same rack in the data center. So I believe the partition is very unlikely unless the rack has caught fire. If the rack has caught fire, the partition tolerance is probably the least of my problems at this point in time, right? And so that's the example Brewer explicitly uses. So he says, you've got to be aware of your circumstance, right? And then, yes, in a cloud environment, you do need to be partition tolerant because you're not on a rack. You've got no guarantee, where the two machines are, and one of them may well fail. But in a data center, maybe you don't have to be. And what he wanted people was to solve the problem, not just declare. When he wrote the original paper, his idea was people will solve this problem, rather than people will just give up. But there you go. So if you've read Captain, I recommend going and reading his paper 12 years later, which is a very interesting read about what he genuinely thinks about the cap theorem problem and the way that it's been used in industry, basically, post that. Anything else? Good. It's warm, so I don't know whether you necessarily want to sit and stare at me for much longer.